EC 201 lecture. Give a quick recap of what happened. We were trying to figure out what the Y parameters of a box like this, which we called an amplifier. In the simplest case, a 3-terminal 2-port network. We were trying to figure out what constraints would be placed on this box if we need to get a large gain, independence gain with respect to RS, and the no feedback condition. And you've seen what feedback can do, and it can basically give you infinite gain, which is not desirable. And what did we see? The incremental Y matrix which satisfies this wish list is given by Y11 is 0, Y12 is 0, Y21 is large, and Y22 is 0. Okay? And in general, we know that this is going to be some kind of nonlinear 2-port. And when you have a nonlinear 2-port, what can we say about the relationship between the terminal voltages and the terminal currents? Please note that this matrix is what kind of Y matrix? It is an incremental Y matrix. It only relates incremental changes in voltage to incremental changes in current. And in any general nonlinear 2-port, what can we say about the absolute voltage and the absolute current relationships? In any general nonlinear 2-port, what are the relationships if you assume that the port voltages are independent variables and the port currents are dependent variables? What relationships govern? So I1 is some function f of V1 comma V2, and I2 is some other function g of V1 comma V2. Okay? And what is Y11? The incremental, it is dou f by dou V1. Okay? Evaluated at the right operating point. Y12 is dou f by dou V2. Y21 is dou g by dou V1, and Y22 is dou g by dou. But we want Y11 and Y12 to be 0, which basically means that dou f by dou V1 equals 0, and dou f by dou V2 must be. Can you think of a function of two variables which will satisfy both these equations? A constant. So in other words, I1 is some I naught, okay, where I naught is, in other words, Y11 and Y12 being equal to 0, all that they impose is that the input port current must not be dependent on either V1 or V2, which basically means that it should be some constant value I naught. That constant could be 0, it could be a microamp, it could be a milliamp, it could be a nanoamp, anything. Okay? I naught is some constant. Alright. Now, what is the next thing that we want? We want Y22 to be 0 and Y21 to be large, which means what? Dou G by dou V1 must be large, and dou G by dou V2 must be 0. Which means what now? What does this mean? G is simply only a function of V1. Does this make sense? So let's see what. So the 2-port equations will be I1 is equal to I naught, some constant, and I2 is some function g of V1, where g is some arbitrary function. And yesterday we saw how do we represent a 2-port graphically. In general, a 2-port has got 2 equations. Each one of these equations is a 3-dimensional representation. And to represent this 3-dimensional thing on paper, it makes sense to actually plot, for example, I2 versus V2 for different values of V1. And similarly, you plot I1 versus V1 for different values of V2. And these sets of curves, which are called the input and output characteristics of this 2-port, give all the information that is required. Okay, that is there in these equations. So now, let's plot the input characteristics. What can you say about the input characteristics now? The input characteristics are very straightforward. The current is a constant for all values of V1 and V2. So there's hardly anything to plot. The next thing that must be plotted are the output characteristics. So the output characteristics. So I would like to plot. So what will be there on the x-axis now? V1 or V2? What are the output characteristics, people? You plot I2 versus V2 for different values of V1. Okay. Now, let's take some arbitrary value for V1 being equal to some delta V. Okay. So how will the characteristics look like? The current in port 2, I2, does not depend on V2. So for a given value of V1, it will be a straight line parallel to the x-axis. Okay. This is the characteristic, for example, for V1 is equal to, say, some delta V. Let me not confuse you by choosing delta. Let me call this, say, VA. Alright? Okay. If I had another value VB, what do you think I would get? I would get another line which is also parallel to the x-axis. Okay? Maybe perhaps like this. And let me just say, instead of VA, let me if you're calling it VB, let's say let's make this 2VA. Alright. When I put V1 equal to 3VA, what do you think I will get? I will get another line parallel to the 2 lines I've already drawn. Can somebody make a comment on the spacing between the new line and... So let me go and draw this new line in red. Okay. Can anybody make any comment on the spacing between the red line and this line? Okay. The red line and this line, and the line corresponding to V1 equal to 2VA and the line corresponding to V1 equal to VA. I mean, can you make a comment or no? You can't make any comment. Why? It depends on G. Okay? Great. So, for example, this is a legal valid set of curves, and so is this. Okay? And so is this. Okay? So depending on the kind of nonlinearity G, the third curve can be any one of these 3 or anything else that I can draw which is parallel to the x-axis. Does this make sense? So let me get back to my black ink. So let me choose some random looking curve like this. So V1 equal to 3A. And some other curve like this, V1 equal to 4A. Okay. This spacing delta 1, this spacing is delta 2, this spacing is delta 3, and in general delta 1 not equal to delta 2, not equal to delta 3. Specific values of delta 1, delta 2 and delta 3 depend on the nature of the function G. If G was exponential, what would you expect? For the same spacing in V1, the spacing between the currents I2 would be rapidly increasing as I increase VA. Okay? For example, another example is, say, if you had a device where G was of the form V square, that would also increase with increasing value increments in V1. However, the increase there would be less steep than the increase when you had an exponential curve. Okay. Now let's take a special class of devices where the input port current, which we found that it must be a constant, let that constant actually be 0. 0 is as good a constant as any other constant. Correct? So, in the special case of I1 being equal to 0, what does passivity enforce on the 2 port? If I1 is 0, if the 2 port has to be passive, then V1 I1 plus V2 I2 must be greater than or equal to 0, but this by construction is 0, so V2 I2 must be greater than or equal to 0, which means that the output characteristics can only lie in the first and the third quadrants. Does that make sense? So to repeat again, in the special case where the input port current, which we wanted to be a constant, if that constant was somehow 0, alright, then passivity of the 2 port forces the output characteristics to lie in the first or the third quadrant. Okay? Great. That means what? These characteristics, this characteristic here, which was parallel to the x-axis, has to go into the third quadrant. Correct? This characteristic can only exist in the first or the third quadrant. The characteristic which was in the first quadrant has to go, which is parallel to the x-axis, has to go into the third quadrant. So how can it go? It has to go through the origin. So which means what? Can the slope remain 0 always? If it has to go through the origin, the slope better do this, isn't it? Okay? So the output characteristic cannot remain parallel to the x-axis for all values of V2. For some value of V2, eventually the slope of the characteristic must change from 0 to some positive value, dive through the origin and go into the third quadrant. Does that make sense? So what can you say about the characteristic? If this was parallel and it has to go through the origin, it has to do something like this. Okay? Similarly, this has to do something like this. This has to do something like this. Do something. You understand? And do these characteristics look familiar to anybody at all? So, all these things came without assuming anything. Alright? From first principles, we've derived what the characteristics of a 2-port, which give us gain, must be. So, then what would I do? I say, hey guys, anybody who's got a device with this kind of characteristic, give it to me, I'll make an amplifier. And then sure enough, the device guys will say, oh, I've got any number of devices which have these characteristics. One of them is the MOS transistor. Another of them is the gallium arsenide FET. Another one is the JFET. Okay? And there are any number of, all sorts of wonderful looking field effect transistors. There's the bipolar transistor. And those of you who have done devices, you learned MOSFETs and have you learned MOSFETs? Have you learned JFETs? You've learned MOSFETs, you've learned JFETs, you've learned bipolar transistors. Okay, or you're supposed to have learned all these three. Is that correct? Is there any fundamental difference between the MOSFET and the bipolar transistor? Do they operate on the same physical principle or no? Have you heard of drift and diffusion? Yes, sir. So, where is drift and where is diffusion? Predominantly in a bipolar transistor, carrier transport happens through diffusion. And so you make the base width small and all this wonderful stuff, okay, which I don't remember anymore. If there is a channel existing, the electrons shoot across because of what? The electric field between the pinch off region and the source. Okay? So, the current flows in a MOS transistor mostly by drift. And if one thing you've noticed, you can see even looking at the bipolar and MOS transistor examples, these are two devices which operate physically in a completely different way. However, the IC versus VCE characteristics of a bipolar transistor and the ID versus VDS characteristics of a MOS transistor look surprisingly similar. In fact, the I versus V output characteristics of any old semiconductor device that you can think of that has been invented over the last 50 years, they all look similar, okay? And they look similar to this characteristic on the board. We don't know anything about Fermi level, we don't know anything about diffusion, and even lesser about drift, okay? Only from basic principles and conservation of energy, we are able to predict that any device which gives us the incremental gain must have these kinds of characteristics. Does that make sense? Okay? In other words, this is a fundamental thing which you can deduce simply from what you wanted and from energy conservation. I mean, the whole reason why I do this is to, take away the impression that, 20 years from now, maybe these transistors won't exist, there will be quantum dot something tunneling, okay, some major nano device, okay, and whatever great device there is, the characteristics will still remain. The G of V1 might change, but the characteristics will still remain like this as long as I1 equal to 0. And I1 equal to 0 turns out is not difficult to achieve at all. Between the gate and the channel there is an insulating oxide, that is why it is called metal oxide semiconductor. So presumably there is nothing that can flow through the oxide, so I1 is 0. Similarly in a JFET it's a reverse bias junction, so I1 is approximately 0. And a bipolar transistor, it's recombination current in the base, where that's also very small, and those of you who have not done devices don't get perturbed, it's in great stuff as far as this course is concerned, because you are able to deduce the characteristics from simply energy conservation and common sense. That's all we used. So as I said, the next job, the next task at hand is to go with a begging bowl to every device guy you can see and say, hey, you have a device which can give me such characteristics, and as I said, lo and behold, there are any number of devices, okay, and anticipating the future, let me call these terminals, instead of calling them ports 1 and 2, I will call them G, D and S. There is a device which satisfies these characteristics, which is not very surprising. One such device is called the MOSFET, stands for metal oxide semiconductor field effect transistor, and it has the characteristics I had shown you before it. The characteristics look similar to this. So this is I1, this is I2, which is also called, now since port 2 has been renamed as D, it makes sense to call it ID. And since port 1 has been renamed as G, I will call this IG. IG equal to 0, alright, and it turns out from the theory of semiconductor devices that ID is given by 1/2 mu n Cox. Please don't get frightened about all these symbols, they're all just symbols. Yeah, when we discussed, we said ID is some G of V1, and as I showed you before, the current in the second port cannot remain independent of V2 forever. There must be a region close to the origin where it must become dependent on V2. Sure enough, if V2 is equal to what in the new jargon? V2 is the same as VDS. Okay. So for sufficiently large VDS, okay, so in other words, for VDS greater than some minimum value, the current is given by this equation on top, and you can see clearly that that equation does not contain VDS. And as soon as the VDS becomes small, you can see that the VDS terms start appearing in the equation, and because it has to go through the origin, you know, if VDS equal to 0, the current is 0. Okay, and that's happening because Ig equal to 0. Alright, let me just familiarize you with the jargon. Mu n C ox, okay, is some physical constant. Mu n is the mobility of electrons. C ox is the oxide capacitance. W and L are geometry related parameters. And as I said, for those of you who have done devices, these equations probably sound familiar. VGS and VDS have their obvious meanings. ID is the current to the terminal D. The terminal D is also called D stands for drain. G stands for gate. S stands for source. Instead of drawing this ugly looking box, you can draw a symbol which just looks just as ugly. D, G and S, and drain current ID flows into the drain just like how it does into the box. So by Kirchhoff's law, whatever current flows into the drain must flow out through the source. So the arrow on the source is indicating the direction of current flow. So as I said, there are any number of G's, okay, that can be conceived. This is just one example of some nonlinear function G. So GS, which is the voltage across port 1, is called the gate source voltage. VDS, which is the potential between the drain and the source, is called the drain source voltage. You have the drain current and then you have the gate current. The drain current by definition must be equal to the source current because no current flows through the gate. For a given MOSFET, the mu n, C ox, okay, and W by L are related to the construction of the device, and as such will be given to you in an exam. So don't have to get perturbed if you don't understand what these numbers are. Alright, as far as you are concerned, half mu n C ox W by L is just the constant you multiply with VGS minus VT the whole square. Okay, the only other quantity that we have not defined is threshold voltage. So VT is the threshold voltage. And the question is, why is it called the threshold voltage? It turns out that ID is 1/2 mu n C ox W by L times VGS minus VT whole square, as long as VDS is greater than VGS minus VT and VGS is greater than or equal to VT. Okay. So if the gate source voltage is less than some threshold, there is no current in the drain. Okay. In other words, the VGS must cross a minimum voltage before current can flow between the drain and source, and that minimum voltage is the threshold. So this takes a little while to getting used to. So that can only happen if you study the notes regularly and work out the tutorial problems. Tutorials will come your way very soon. Let's quickly evaluate. So ID is 1/2 mu n C ox W by L times VGS minus VT the whole square. For VDS greater than or equal to VGS minus VT, and VGS greater than or equal to VT. So provided these two conditions are satisfied, that is, these two conditions are satisfied, what is Y11? Y11 is 0 because what about Y12? What is Y12? That's also 0, and both of these are 0 since Ig is 0. Okay. Then what about Y21? What is the definition of Y21? I2, what was I2 is now ID by dou VGS. And what is this now? Mu n C ox W by L times VGS minus. So you can see that when VDS is greater than VGS minus VT and VGS is greater than or equal to VT, okay, the current in the drain remains constant and is independent of VDS. Okay, this region of operation where VDS is greater than VGS minus VT is called the saturation. This is device jargon. Okay, so in other words, let's try and plot this curve. So ID versus VDS for a given VGS. If VGS is less than VT, we said that if VGS is less than the threshold, the current is 0 always. Okay, so this all these curves are basically VGS less than or equal to VT. So now if VGS is greater than VT, what happens? Let's say we have some VGS1 which is greater than VT. Then beyond a certain point it will be constant, so it will be parallel to the x-axis, and the value of this current will be 1/2 mu n C ox W by L times VGS minus VT. And what can we comment about this part of the curve? Here in this region, it is parallel like this, it must go into the third quadrant, so what must it do? It has to pass through the origin, and if you actually look at that equation, you will see that it is a parabola. It does something like this. And this value of VDS, which is the minimum VDS required in order to keep the current in the drain independent of the drain source voltage, what is that value? Look at the equation and tell me. VGS minus, this is VGS1, so this is going to be VGS1 minus VT. So if I increase VGS1, what will happen to the current? If I do the same experiment now for a VGS2 which is greater than VGS1, what will happen? Okay, so one thing is that the current, so this is the saturation region. Okay, so this is the saturation. Okay, and why do you think it's called the saturation region? So one way of looking at it is, okay, I go on measuring the current in the drain as I go on increasing VDS. So I increase VDS, the current increases first. I increase VDS some more, the current increases even more. So I start getting greedy and increase VDS a lot, and then I find that the current doesn't increase. The current saturates, so it makes sense to call it the saturation region of operation. Now if I apply another voltage VGS2 which is greater than VGS1, the saturation current will be higher. Okay, so this is 1/2 mu n C ox W by L times VGS2 minus VT the whole square. Okay, and again this must go to the origin, so it must do something like this. So can you comment on where the second curve enters saturation versus the first one? it will enter saturation later. Okay, so that value will be, does that make sense? So if I now draw it for VGS3, it will be another curve like this, and it will do this. Okay, clearly the saturation current is higher than in the first two cases, and it also enters the saturation region for much larger values of VDS. Okay, so this is going to be VGS3 minus VT. It makes a lot of sense to spend time, think about these equations and be familiar with stuff rather than every time looking at these equations for the first time. Okay.